Hello, I'm Junqiao. In this talk, I will show you how we can break the dependencies in Bitstream programs and make them run in parallel automatically. We call our approach principal bitwise speculation. This is the joint work with Jiang and my advisor, Dr. Zhijia Zhao. First, what is Bitstream processing? These are computations that involve many bitwise operators, such as logical AND, OR, shift, etc. Furthermore, they consume and produces sequences of bits called bitstreams. We refer to the programs that implement the bitstream processing as bitstream programs. Bitstream processing is widely used in many performance-critical applications, such as multimedia data decoding and bitmap indexing. The links here show some bitstream kernels used in real-world applications. Some of them are used for decoding multimedia data, such as images and voice records. Some others are used for processing texture data, like XML, JSON, network traffic, or DNA sequences. The main reason they adopt bitstream processing is usually for better efficiency in terms of both time and space. Not surprisingly, bitstream computations may carry dependencies. This is often caused by the use of some special bitwise operators, like the lab or right shift and the arithmetic addition. Take the arithmetic addition as an example. Clearly, there is a dependence regarding the carry. The addition of the two current bits depends on the addition of the prior two bits. The existing efforts in optimizing such computations often rely on fine-grained parallelism. For example, rather than processing the bitstreams bit by bit, they process them byte by byte, word by word, or even vector by vector with the help of SIMD instructions. However, this often creates new complexities. For example, it's even harder to tell if there's a carry or not when two bytes are added. To answer this, it requires a significant amount of logical operations, as shown in the pseudocode of long bitstream addition here. Moreover, at high level, the loop is still executed in sequential. So our goal of this work is automatically parallelize this bitstream traversal loop, regardless if the code already uses fine-grained parallelisms or not, like the SIMD instruction. To achieve this goal, our idea is to reduce the parallelization of bitstream programs to an existing problem. That is the parallelization of the finite state machine, even though they appear to be totally different kind of computations. As we know, finite state machine is an abstract computation model with some states and transitions. The transitions can be drawn as a direct graph. The FSM starts from an initial state and consumes an input symbol each time to make a transition. In recent years, there have been a series of work on parallelizing FSM computations, and many of them have achieved very good performance improvements. I will provide more details about these existing works later. So, if we can convert bitstream programs to FSMs, then we can reuse these existing techniques to automatically parallelize them. Originally, our idea of reducing the bitstream programs to FSMs was inspired by the fact that both bitstream programs and sequential circuit process binary sequences. Moreover, the dependencies in sequential circuit can be captured by the next state logic. So, a natural question is, can we model bitstream programs with FSMs? And the answer is yes, but how to achieve that is non-trivial at all. To model bitstream programs with FSMs, we propose a three-step approach. First, we need to find out the bits in the program variables that cause dependencies. Then, based on the dependent bits and bitstream program logic, we generate the truth table. Finally, we convert the truth table into an FSM. Note that in circuit design, we actually first design the FSM and then convert it into the truth table. Here is the opposite. Now, let's look at the first step. identify the dependent bits. The idea behind the static analysis can be explained with a few observations. The first observation is that the dependent bits should be used before defined in the loop body. With program analysis terminology, we say these bits are live at the entry of the loop body. On the left example, in the loop body, a variable A is first defined and then used. Then the dependence happens within the same loop iteration rather than across loop iterations. So the bits of variable A do not create any dependence across iterations. In comparison, on the right example, where variable A is used at first and then defined, which implies that the use of A in this iteration depends on the definition of A in the previous iteration. In other words, it introduces loop carry dependencies. So, X bits are the candidates of dependent bits. The second observation is more specific to the bitwise computations. In fact, due to the use of bitwise operators, some bits in a variable may not be actually used. Take a look at this AND operation. Because the 5 most significant bits of 7 are 0, the 5 most significant bits of variable B do not contribute to the results. No matter what values they have, the 5 most significant bits of A are always 0. So, this irrelevant bit should be excluded from the dependent bit set. Furthermore, to know if some bits are actually used or not, we need to find out. At first, some bits in variable are constant. Consider this AND operation between A and D. If we know that the 5 most significant bits of A are zeros, then we can tell the corresponding bits in D are irrelevant. So, the analysis of irrelevant bits depends on the analysis of constant bits. And finally, we should exclude bits that are read-only, as they never introduce any data dependencies. Put the above observation together, we developed a series of static analysis and came up with the equation to integrate their results. Basically, we find that the dependent bits should be live at the entry of the loop body. Meanwhile, their values should be unknown and may be changed in the loop body. For these small running examples, the analysis can narrow down the dependent bits to the first 3 bits of variable C. Based on the dependent bit reporting, now we need to consider how to generate the FSM, which requires constructing the states and transitions. First, with the dependent bit, we can introduce the states. Basically, we encode each binary combination of the dependent bits as a state. For example, if we have 3 dependent bits, we have 8 states. But how about the transitions? To find out the transitions, we use a truth table-based approach. Here, the first 11 columns enumerate all the value combinations of dependent bits and input bits. For each combination, we run the bitstream programs to collect the new values of the dependent bits, which essentially provide us the next state logic. Each row here actually corresponds to an FSM transition. We simply need to replace the binary values with the corresponding states and add an arrow between them. In this way, we convert the truth table into the FSM. Again, in circuit design, usually we first define the FSM and then convert it to the truth table. Here is the other way around. But there may be some FSMs and truth tables that are too large to generate in practice. So we introduce partial and virtual FSMs. The intuition of partial FSM is, in many applications, the wasting frequencies of FSM transitions are biased. So it is possible to use a small portion of the capture transitions to cover a large number of actual transitions. To achieve this, we use a pool of training inputs to collect the hot values of dependent bits and input bits based on the appearing frequencies. Hence, a partial truth table is first constructed, and then following the truth table to FSM construction, a partial FSM is created. Another way to adjust oversized FSMs is to completely bypass the physical FSM constructions. We simulate FSM transitions with the execution of Bitstream program. Basically, an FSM transition is virtually performed with the execution of the main loop body of the Bitstream program, where the current state is the current values of dependent bits, and the next state is the resulting value of the dependent bits after the execution. In this way, there's no need to generate the truth table. Anyway, when it is possible, it may still be more beneficial to generate the FSM physically, as we will see shortly in the evaluation. After modeling the Bitstream programs with FSMs, now we can use the ideas of FSM-based speculation for parallelizing the Bitstream processing. As I mentioned earlier, there exists a rich body of work on FSM parallelization. Similar to the loop carry dependencies in Bitstream programs, FSM-based computations are also sequential in nature. In each state transition, the current state is updated based on the prior state and the current input symbol. So that's the chain of dependencies. One way we can break the dependencies is, after splitting the input sequence into chunks, we make a prediction for the starting state of each chunk, except the first one, where the starting state is known. Then, with the predicted starting state, we can process the divided chunks in parallel. If the prediction turns out to be correct, then we have finished the whole processing. Otherwise, we need to reprocess the second chunk. This technique is known as speculative parallelization. It breaks the dependencies with prediction, then relies on reprocessing to ensure the correctness. Previous research has found that we can leverage the state convergence property of FSMs to improve the efficiency of this speculative parallelization. The idea is we start from all the states of the suffix on the suffix of the prior chunk, and after processing this small piece of input, we may notice some states are merged into the same state. In the best case, all states transitions to the same state. Then we already know the correct starting state. Otherwise, we may pick up the one that appears most frequently. We call this look-back-based speculation. So, the parallelization of Bitstream processing is pretty much the same as FSM speculation technique. The only difference is that after predicting the starting state, we need to decode it into the binary values and assign them to the corresponding bits in the program variable. So, at high level, in the proposed principal bitwise speculation approach, given a Bitstream program, we first use static dependent bit analysis to find out the dependent bits. The analysis is implemented as an LLVM pass called depend bit. Then we use the truth table approach to generate the FSM. And finally, we leverage FSM speculation to enable parallel execution. In our current prototype, both the FSM generator and speculation runtime are implemented as standalone module using C++. We evaluate PBS on a 64-core machine equipped with an initial Intel with an Intel Gen 5 processor. The machine supports SIMD instructions like SSE and AES2. We use the recent LLVM compiler for analyzing the source code and GCC compiler for generating the executables. The benchmark used include Bitstream kernels and an open source high performance regular expression engine. The evaluated Bitstream kernels are collected from multiple applications, ranging from semi-structured data processing and text pattern matching to multimedia and bioinformatics. 3 of them are implemented with SIMD intrinsic. For each kernel, we collected a set of inputs from their applications, including 10 small inputs with 10 megabytes each, and 10 large inputs with 300 megabytes each. To demonstrate end-to-end benefits, we also evaluate PBS with a regular expression engine called icgrep. The engine has been commercialized by researchers from Simon Fraser University. Basically, for each given pattern, the tool generates a bitstream program to find the pattern. The input texture streams are collected from a Linux server TCP dump with TCP dump tool. This table shows the analysis results on the bitstream kernels. We can see that the number of dependent bits is usually quite small. This is mainly due to the nature of bitstream computations. The use of bitwise operators can significantly reduce the amount of dependent bits. During the evaluation, we also discovered a couple of interesting findings, which can be also used for additional optimization. First, unlike FSMs, the output of bitstream programs are binary sequences. Under certain conditions, the correct and incorrect output bitstreams may be correlated by some bitwise computations. For example, we find that in a bitstream kernel, the incorrect output bitstreams could be exactly the opposite of the correct output bitstreams. Another interesting finding is, for some bitstream programs, the generated FSM runs sequentially even faster than the original bitstream program. This means we can even accelerate the sequential bitstream processing. Then take a look at the speed up from parallelizing with optimization. In general, for the large inputs, the speed up tends to be higher because with larger inputs, the parallelization costs, such as the flag creations, can be better amortized by the longer executions. In specific, for 4 bitstream kernels, we observe near linear speedups close to 60 times. On average, the speedup is about 40 times. There are 2 main reasons for the sublinear speedups. One is the limited speculation accuracy. For kernels CROSSTREAM and AB10B, they have a low speculation accuracy, around 50%. But due to the fast recovery optimization, CROSSTREAM is able to reach over 32 times speed up. And by replacing the original bitstream processing with FSMs, AB10B can reach over 43 times speed up. The other reasons for the sublinear speedup is that some bitstream kernels are also I/O bounded. In this case, the speedups are capped by the I/O operation, like writing to the memory. As for the scalability, 4 kernels present near linear speedup up to 64 cores. And in general, the scalability mainly depends on the speculation accuracy with processing cost and I/O to computation ratio. As for the evaluation on icgrep, first, our dependent bit analysis shows that the number of dependent bits range from 19 to 36. In general, for more complex regular expressions, the number of dependent bits tends to be larger. Given the relatively large number of dependent bits, we apply the virtual FSM-based speculations. We can observe that their maximum speedups range from 10 times to 27 times. The speedup comes from the high speculation accuracy, which is about 100% speculation accuracy. The sublinear speedup are due to the generation of output bitstreams, which are saved in cases that the user wants to print out the mesh context. Note that these are not the kernel speedup, but the end-to-end speedup with all the computations included. In sum, in this work, we show that with the adoption of proposed systematic treatment, principal bitwise speculation, the bitstream carry dependencies become breakable in many cases. From another perspective, this technique, for the first time, generalized the FSM speculation techniques to more general programs. Finally, our evaluation with real-world bitstream programs confirms the effectiveness of PBS and the efficiency of parallelized programs. Thank you.